Okay, welcome back to this second part in the 5-part tutorial to derive the critical t-value from and to derive the student's t-distribution. So in the second part, we're going to actually derive student's t-distribution. I'm going to go a little bit faster. This part's a bit more math heavy. You're going to have to understand some basics about calculus and probability distributions, and I'll just get started. So in this part, we're looking for the distribution that defines the t statistic. So we're looking for the distribution that defines the t statistic. So what is the t statistic? Well, suppose that we look at the distribution of our average values to the real mean value, and we do that using the real population variance. Well, this value is going to be distributed according to the normal distribution. And the question is, what happens when we replace our sigma, which is the real population variance, with the sample variance, S sub n. That is going to give us the so-called t statistic, and that's defined to be merely this value. So this thing is distributed according to student's t distribution, which is formally written out like this. And student's t distribution with v degrees of freedom. That's written that way. So we are going to derive the probability distribution function for the t statistic. And we're going to start by recognizing a few things about the t statistic as we've defined it. So first of all, recall the definition for S, which if we write S squared, it's merely the sum of squares of this term, all over n minus 1. The question arises, how is this particular value distributed? Well, I can show you that if we define a new random variable as these, that these are distributed according to a standard normal distribution with mean 0 and variance 1. And if you take the sum of, if you take a sum of squares of normally distributed random variables, you get something which is distributed according to the so-called chi-squared distribution with v degrees of freedom. So what we know is that this is distributed according to the chi-squared distribution. And we're simply going to call this s squared term y. Now what we have is the t statistic in terms of easier to work with, more fundamental, simpler random variables. But we're not done yet, because what we need to do is we need to define that denominator term in simpler notation. So for the numerator, if we define it to be merely this, we know that this is distributed according to the standard normal distribution. And in that sense, if s squared is distributed according to the chi-squared distribution with v degrees of freedom, and we're calling s squared y, then we can rewrite the t statistic as z over the square root of y over n. And recall the definition for a standard normally distributed random variable. The distribution is merely this formula, everyone's favorite Gaussian, with the normalizing constant square root of 2 times pi. So the question then becomes, what is the resulting distribution given the ratio above, right? And that will give us our student t distribution. And this part gets a bit math heavy, but nothing we can't handle. We're going to use what is called the change of variable formula for probability distributions. And I'm going to simply use it, and the definition will follow. So we have the distribution for y. That's the simple chi-squared distribution with v degrees of freedom. And we want to know, what is the distribution for the square root of y? In other words, we define a new random variable y hat. The question is, what is the probability distribution function y for y hat? Well, this follows from the change of variables formula. And we can show that if y hat is the square root of y, then the function transforming y is merely equal to y hat. And our formula says the new distribution is equal to the derivative, the absolute value of the derivative with respect to y hat of the inverse transformation multiplied by the old distribution evaluated at this inverse value. Now we have to figure out precisely what is the definition of a chi-square distribution with v degrees of freedom. This is simply y v over 2 minus 1 times e 2 and gamma v over 2 times 2, just like that. So now we can take the derivative, take the inverse, which is simply, how do you undo a square root? Well, you square it, and we can evaluate this probability density function as the derivative of y hat squared times y hat squared over 2, and this constant stays. So that's the answer, and we're just going to simplify this. This becomes 2y hat times this term, which simplifies again because this y hat will cancel, and then the 2's will one of the 2's will cancel, and we're left with a new distribution for y hat, which is equal to this distribution. I'm going a little fast here. I apologize for that. And this is only partially done because we still have that square root of n term. So we have the probability distribution function for the square root of y, but now we need the square root of y divided by the square root of n. So we're going to define a new random variable, x, and we're going to call it y hat divided by the square root of n. Now, foreseeing a little bit, we're going to just take the derivative with respect to x. We're going to get square root of n. And we're going to define now our new probability density function in terms of the old with a new argument and this absolute value. And then we're just going to simply evaluate this. And this turns out to be this value. And you can check this arithmetic, or algebra, it's all fairly simple. We have this expression, and we're going to simplify this. And the simplification comes out to be, the one we want at least, looks a bit like this. Okay, so from this definition, we can now write the t-statistic in terms of simpler random variables. The first of which is that normally distributed numerator, and now we have a new random variable x. And what we want is we want the result, we want the probability distribution function for a ratio of probability distribution functions, that associated to z and that associated to x, which we just calculated. So here we're going to utilize what's called the quotient rule for probability distribution functions. And this is also called a Mellon transform in functional analysis. And I'm just going to write out the definition real quick. And again, this is all fairly rudimentary, and you can find this information online or in a class on probability, perhaps. And this is simply the definition. So now we have an integral in terms of the two probability distribution functions we derived. And what's nice is if you take a look at the probability distribution function with respect to x, you notice that it's equal to 0 on the domain from -infinity to 0. And then x being positive between 0 and positive infinity, we can actually rewrite this as the integral from 0 to positive infinity of x times our distribution functions, which we've derived above. And now we can actually write this out in full using our definitions. So now just plugging in for the new arguments, we get x over the square root of 2 pi times e to the negative xt squared over 2 times 2, 1 minus v over 2 all over gamma of v over 2 times v over 2 times x v minus 1. And again, I'm just plugging in our definitions for the transformed probability distribution function, chi-squared, and the standard normal distribution. And this allows us to write an integral form for the student t distribution, and it looks like this. And this is fairly nice. These are just constants that come out. They're not part of the integration. They're just multiplicative constants. And we can get this integral, which we'll evaluate in a second. And this is an integral form of the probability distribution function of students' t distribution. So I'm just going to put this in a box because it is fairly nice. It's a fairly nice answer. And next we're going to actually evaluate this improper integral on the right-hand side.